I have solved this problem in class. I'm just going to solve it again in here, but I'm going to go over the steps a little bit more quickly. So we have an infinite line of charge, infinitely thin line of charge, so it's given like this. So the thickness is assumed to be 0. It is a uniform charge density lambda, and we have a point in here which is at a distance r from the line, and we would like to find the electric field at that point. In class, I have used capital R for that distance symbol, but in here I'm going to use little r because usually for radial coordinates, for distances, we use the little r symbol. All right, let's quickly go over. So this is the essential picture in here. So there was this option in here whether we can parameterize the line with a Cartesian coordinate x like that, where that's the x-axis, or we can use a parameterization by using this angle, theta, right? And then I have said that theta is more appropriate, right? Let's then talk about this. It's actually kind of appropriate to use both of these coordinates at once in the first derivation stage. So therefore this is x. I know that x is equal to little r times tangent theta, and what I do is I just choose a small segment of charge in here. So this segment of charge is seen by an angle of d theta from here, so that's d theta. And I would like to, I'm actually considering about the length of that segment in here. This is dx. I can compute this by just taking the differential. So the differential of tangent theta is 1 over cosine square theta times d theta. If you want, this is basically the derivative of x with respect to theta. Right, let me just write it down like that. So you can use the differential calculus that you have learned in calculus in here to compute these kind of quantities. So why do I need dx? Because I need to find the amount of the charge in here. So the charge on that segment is basically the linear charge density multiplied with dx. So that's equal to lambda r divided by cosine square theta d theta. What else? I also need that distance in here. This is the distance that I'm going to need to use in Coulomb's law. So that distance is, I know that this is little r divided by cosine theta. Right, what else? Let me use the blue color for the electric field. So there is an electric field produced by that segment at that point. So since this electric field is small, we show its magnitude by dE. We use d to show that it is really small. Let's just remember that this angle is theta. This has an x component like that. Sorry. Let me show it like this. This is dEx, and it has a y component like this. I'm interested in the y component because I know that at the end the electric field has no x component. In any case, so I'm going to write them down. So dE, first of all, that's basically given by the Coulomb's law. This is just the magnitude. I'm just writing down the magnitude. Right, let's then simplify this. So dq is given by this expression in here. So let's write this thing down. So that's lambda r divided by cosine square theta d theta. And then I need to divide this by the distance squared. So that's r divided by cosine theta squared. And when you compute this, then the magnitude of the electric field at that point would be lambda divided by 4 pi epsilon 0 r times d theta. Okay, so by itself, this doesn't mean anything. It's just the magnitude of the electric field produced by a small segment. But now I actually need the y and the x components. So let me quickly write them down in here. So dEy is equal to dE times cosine theta. And the x component is, I just noticed that there's a negative sign in here. minus sine theta. Okay. At the end, I know that this is a zero integral, so therefore this is the one that I need to concentrate on. So let's quickly do this. Ex is equal to the whatever. At the end, I know that this is going to be equal to 0, so therefore I don't bother computing it. And the y component is obtained by summing over all of these y components produced by each infinitesimal segment. And so that's equal to the dE times cosine theta. Let's write dE. It is given by this expression in here, right? We have already found the expression. So that's lambda over 4 pi epsilon 0 r d theta. And then I just write it down like that. And finally, I just noticed that the angle theta in here ranges from minus 90 when the point is at minus infinity in here, so in which case my angle goes to minus 90 degrees, which is minus pi over 2 radians, and plus infinity, so my segment is going at the plus, is at the coordinate x equals plus infinity, in which case that angle would be plus 90 degrees, which is plus pi over 2. So my integration boundaries are minus pi over 2 and plus pi over 2. This is just a constant meaning that it doesn't depend on the variable theta in here. So these are all expressed in terms of the given quantities. So lambda and r are given, just keep this in mind. So that means I can take this thing out. So that's basically the part of the integral that we don't need to be worried about. So there's an integral of cosine theta. So the integral of cosine theta is sine theta. So I just need to compute the sine theta between these 2 points. So I know that this is sine pi over 2 minus sine of minus pi over 2. Sine of 90 degrees and minus 90 degrees. So I know that this is plus 1 and I know that this is minus 1. So therefore the integral is equal to 2. So that means the y component of the electric field is lambda over 2 pi epsilon 0 times r. Right? I know that this is also the same thing as the magnitude of the radially outward component of the electric field. That's, instead of saying magnitude, we should actually say it like that, or the y component. So therefore this is what I write. Okay, so that's the whole problem.